what we talked about was that there's nothing special about colors. What happens is that you have all sorts of electrons, and those electrons are all getting into excited state, which means that they are absorbing energies. And when they absorb energies, those frequencies, they kind of go missing, which is why the observer cannot see those frequencies, which is why the observer sees the complementary color. So if you see red, that means red is the only frequency that the substance did not absorb. And then we talked about the D-subshell splitting up. We talked about what's so special about transition metals. And the special thing was that when a complex is formed, you have the D-subshell is inside the atom. It's close to the nucleus. It's got nothing. You have a copper +2 ion, which has a D-subshell that is residing inside it. The water molecules are attracted on the outside. So water have lone pairs. These ligands, they come in. And these lone pairs, they exert a force of repulsion, which is why it's a lot harder to keep electrons in the green orbitals, the ones that are lying on the axis. And it's a lot easier to keep electrons in the pink orbitals, which are between the axis. So the D-subshell, which was previously degenerate, which meant that all orbitals had exactly the same energy, it split into two energy levels, two separate energy levels. One are the green ones, which are lying on the axis. One are the pink ones, which are lying between the axis. Easier to keep electrons over here, difficult to keep electrons over here. So the electron has to be more energetic. And there's an energy gap. And what happens is that luckily that energy gap exactly matches frequencies that belong to the visible spectrum. So if an electron wants to jump from a lower energy D-subshell to a higher energy D-subshell, it is going to absorb a certain frequency from the visible spectrum, and that frequency belongs specifically to one of the frequencies that belongs to the visible spectrum, which is why you see colors, because some frequencies go missing from white light. So if it absorbs red, you see something blue. If it absorbs blue, you see something that is red in color. So so this was the whole explanation, that due to repulsion from lone pairs or ligands in metal complexes, the D-subshell splits into two energy levels, and electrons from the lower energy d orbitals gain energy and move to higher energy d orbitals, and the energy gap matches frequencies which are part of the visible spectrum. This is the exact answer that you're going to quote, and pretty much in every exam they ask you about this. They ask you, it's a 3-mark or a 4-mark explanation for this. The other thing for this, a necessary condition for this is that the D-subshell has to be incomplete. It's got to be, has to be incomplete. Only then can this transition happen, that electron can jump from a lower energy to a higher energy D-subshell. There must be room available, there must be space available. So that's one thing. Then the other question that is frequently asked is, why do different complexes have different, or why does changing ligands so why does a change of ligands changes the color of the complex? So the answer to that specific thing is that that different ligands exert a different amount of repulsion on the D-subshell. And the lone pairs specifically, they exert a different amount of repulsion. which creates a different energy gap when the D subshell splits. So it creates a different energy gap as the D subshell. So as the D subshell splits, and again, since E is equal to HF, a different frequency is therefore absorbed from the visible spectrum. From the visible spectrum. So different ligands will exert a different. So copper with water is going to be blue in color. But if you change the ligands, so this one is blue in color or pale blue, and copper with NH3 is going to be dark blue. So that kind of indicates that the energy gap is now different. So a different frequency is getting absorbed. So this one is
Sir,
Hanji.
what's H in E equals HF? What's H?
H is just a constant. It's just that energy is proportional to frequency. TK. H is known as the Planck's constant. You don't have to think about it. TK. You can just write E is proportional to F. So then about this, remember that an octahedral complex, when you have an octahedral complex, you also got to remember this, that in an octahedral complex, the D subshell, if I can just copy this, in an octahedral complex, the D subshell splits up, and let me just copy this. So this is how we learned that in an octahedral complex, the D subshell splits up in this way. But in a tetrahedral complex or any other, remember in an octahedral complex, the ligands are approaching the copper ion on the axis. But that is not true for a different shaped complex. Like if we did all these other types of complexes like tetrahedral, the one that is drawn over here. In a tetrahedral complex, the ligands are not approaching on the axis. So the D subshell splitting is going to be different because they're coming between the axis. So it's harder to, I mean, the angle is 109.5. So none of the lone pairs, none of the ligands are approaching on the axis. So you've got a D subshell over here inside the copper ion, and that D subshell is going to split in a different way because now there's going to be more repulsion between the axis because the ligands are approaching at an angle, not on the axis, not 90 degrees. They're coming somewhere in between. So unlike in an octahedral complex. So the D subshell splits up in the exact opposite way for a tetrahedral complex. Unlike octahedral complex, everything remains kind of the same, except that it's harder to keep electrons between the axes, 3dxy and 3dxz and 3dyz. It's harder to keep electrons over there and easier to keep electrons on the axis, 3dx squared minus y squared, and in the 3D, z squared. And there's going to be and there's going to be an energy gap, delta E, exactly as before. So there's this difference that you have to remember. So I'll write this down. This is for a tetrahedral complex. Ligands approach between the axes. So it's actually harder to keep electrons between the axes. Aisa, I'll send you the recordings for the entire topic. So this one is for a tetrahedral complex. You can rub all of this. So this one is for an octahedral complex. Because all the ligands are approaching on the axis. So just remember the two different splitting patterns of the D-subshell. Is this clear, this part? Is this all clear?
Yes, sir.
So everyone else is, Zoa, is this clear? Sam, Nadine, is this clear?
Yes, sir.
Now the very last part is where's the syllabus? So the only thing that's left is polarity for case, just a second, case stability. Yes, the chapter is over that. So the last part is describe the type of stereoisomerism shown by complexes, including those associated with bidentate ligands. We've got to discuss cis-trans. So these two, okay, that's fine. So now remember in when it comes to so geometrical and for optical, he's talking about specifically about this one and the one with water as well. Okay, that's fine. So we're gonna be very specific. Remember, isomerism in transition metals, it's a big chapter. Like if you go and watch any YouTube video, there are lots and lots of different versions of isomers. And we're talking specifically about stereoisomers over here. So the first thing is, so we're going to stick to the only examples. You don't have to go into a lot of detail. We'll just do those couple of examples and you're going to stick to those examples. Remember, the scope of this thing is it's a huge topic of with lots of examples, but we're going to stick to some simple ones. So starting with what is stereoisomers? Stereoisomers are when you have the same exact structure. The structural formula is exactly the same. So stereoisomers. So that means you have the same molecular formula and also the same structural formula. So they're bonded to the same things, except that the orientation of bonds. So you have the same structural formula, but the orientation of bonds in space is different. So orientation of bonds in space is different. So the first one we're going to talk about is we're going to talk about cis and trans isomers. So cis and trans isomers. So let's keep it simple. Cis and trans. Cis simply means, in simple words, it simply means same side. Trans means opposite sides. Even the cis trans version, like even in the cis trans that you studied in AS, in organic chemistry, it comes with many different names. But we're going to stick with cis trans, with the cis trans naming specifically. So the first thing is we're going to talk about cis trans and square planar molecules. So in square planar molecules, what's going to happen is that we're going to talk about cisplatin and transplatin. So I've got a platinum ion, platinum 2+. It's attached to a Cl. It's a square planar arrangement. So on two sides, you've got a Cl -1. And it's lone pairs. And on two sides, you got NH3. And it's lone pairs. Now, this specific version we're talking about, that's a cisplatin. These are cis because the Cls are pointing in the same direction. So this one is specifically known as cisplatin. The overall charge on this entire thing is 0, because the Cls are -1 and the platinum is +2. It's NH3. Okay, there's an ammonia ligand. There was an ammonia that was floating around. Ammonia has lone pairs. So platinum has a charge of +2. So the lone pairs of ammonia, they get attracted to the platinum ion and they end up forming a dative coordinate bond. So it's NH3. Okay, is this clear? So baki ye ke, 1 second. Here's your cisplatin. And the other one is the other version of this. That's a trans one. So in trans, what happens is that the Cls are on opposite sides. You have the same exact structure, except the Cl, and I would have to change the position of the lone pairs. So the Cl is at the top, so they're opposite sides. The Cls are making an angle of 180 degrees now. And the same goes for NH3. It's lone pairs, they come in and they get attracted to platinum 2+. So over here, they're on opposite sides. So that's your transplatin. So that is one example of cis-trans isomers. So in square planar cisplatin molecule, this is the formula of this is platinum with 2 Cls and 2 NH3s. And the overall charge is 0. So that's the first example. We did discuss cisplatin as being an anti-cancer drug molecule earlier. So that's one example. That's one example of cis and trans isomers. And I can just circle that same side and different side. So the Cls are on the same side. Now the Cls are on opposite sides. The circles are just to highlight the fact. So then you have another one, which is in octahedral complexes. So we're going to talk about cis and trans isomers. So cis and trans isomers in octahedral complexes. So for this, I would have to copy one of the, which one specifically are they talking about? They're talking about cobalt with 2 water molecules. So I just copy one of the complexes that we had drawn earlier. So not this one, just a second. Just hold on a second. My board has hung up. Just wait 1 minute, it's hanging up. It cached. So let's just copy this one. So we have an octahedral complex. They were specifically talking about cobalt, but this is kind of exactly the same, copper. And 2 of the water molecules are now actually, there was some ligand exchange and they are now replaced by NH3. So here's one example. Now this one is the cis version of this particular complex, copper with 4 water molecules and 2 NH3 molecules. And the overall charge is +2. So that's one version. Why? Because the 2 NH3s are pointing to the same side, like they're 90 degrees apart. So one is on the z-axis on top, the other one is on the x-axis. The other version of this is the trans version of the same molecule. The trans version is this one, where the NH3s are going to be on opposite sides. So you got an NH3 and the water molecules. Let me just redraw the. So the water molecules are on the x and y axis, or they could be on any axis, except for the fact that the NH3s are now opposite to each other. Previously, they were 90 degrees apart, and now they are 180 degrees apart. So that's your trans version. Okay, so you've got cis, and you've got trans versions of an octahedral complex. Now, for this to happen, you would at least need 2 ligands which are of a different type. At least that's the minimum requirement. You need 2 ligands that are different. You can get the same arrangement for if you have 3 ligands of one type and 3 ligands of another type. Even then, you're going to get these stereoisomers. So we can do this for 3 ligands, except for the fact you don't call them cis-trans, you give them a different name. That naming is not in your course, but they might ask you to draw the 2 isomers. So what if you had 3 NH3s? So if you had 3 NH3s, then it would look something like this, that the 3 NH3s would all be next to each other, 90 degrees apart. So that's going to be one version. Just a second, I drew it on the This was actually water. So this one. Let's have 3 ligands of one type and 3 ligands of another type. So this water is gone and replaced by NH3. So I've got NH3 and its lone pairs over here. So the 3 ligands, you can remember it's an octahedral complex. These are all X, Y, and Z axis. So I've got 3 water molecules and I've got 3 NH3 molecules. And I'm going to make the adjustment over here as well. Now we've got 3 ligands of one type and 3 ligands of another type. So that's one version. The other version is there are at least 2 of those ligands. So I'll get rid of 1 water. Now again, I've got 3 ligands of one type and 3 ligands of another type, except that at least, 2 of the NH3s are facing or pointing opposite to each other. So that's another stereo isomer of the same molecule. But you don't use the word cis and trans. There's another naming, which they're not going to ask you about, but they might ask you to draw this. Like they might give you this particular formula, and they might ask you to draw the two isomers of this molecule. So the 2 of them are the ones that you see in front of them. This one is specifically in your syllabus, where you have 4 ligands of one type and 2 ligands of a different type. So the 2 NH3s could be together, or the 2 NH3s could be facing opposite to each other. So that would be 180 degrees. One of them is cis and the other one is trans. But this can be asked as well. So is this clear, this one?
Yes, sir.
Then isoligand is this thing. Ligand is you have a copper ion and it's floating around in solution. So these molecules that get attached, they're lone pairs, they get attracted to the copper 2+. That thing is a ligand. Okay, I'll send you all the video lectures. Then the last one. They even talked about bidentate ligands as well. So we can I would have to draw this just a second. Let me draw this very, very quickly with a bidentate ligand, TK, which is kind of the same thing. What I'll simply do is not this one. So I'll just copy this one. So they asked us to show the same thing using a bidentate ligand. And the specific molecule they were talking about was the diamine with 2 water molecules. So it was diamine with 2 water molecules. So kind of the same thing. I'll just make adjustments over here. A bidentate ligand was this, that you had NH2, and the 2 were connected together by a carbon chain. So there was CH2, and then this C was connected to. So that was a bidentate ligand. So they're saying that there are 2 bidentate ligands. So I can remove this, and I can have another bidentate ligand. So I've got NH2 and its lone pairs, and there's another NH2, and the 2 are connected together by a carbon chain. So that's one version, and the other version is this one is your cis version. And the other version for bidentate ligands is you can remove this. So the other version is that the 2 water molecules can be opposite to each other. And the bidentate ligands could be on these axes. So you got NH2, NH2, and they're connected together with and you got another NH2. So they're connected together. So that's your transversion. So we've shown that using bidentate ligands as well. So bidentate ligands were nothing different. They were kind of the same thing, except the two sides were connected together by a carbon chain. It was a much bigger molecule. I said then there's this last one, which is we've got to show. So we've got to show optical isomerism. Now, optical isomerism was what was optical isomerism? In AS, you studied that optical isomerism is when you've got mirror images, you've got enantiomers. So optical isomerism requires chirality. So optical isomers, they were two non-superimposable mirror images. The isomers were non-superimposable mirror images. So instead of wasting time, I'll just Google so this one. It happens. So maybe just a second. Let me see if there's a. So this one is a good example. So I'll just copy this. So this one, the first one, and let's copy another one. Maybe this one. So optical isomers, two non-superimposable mirror images. Now, it usually happens with bidentate ligands. Optical isomerisms, they happen with bidentate ligands. So you got an octahedral complex. This one kind of shows this. You got an octahedral complex. Now, hopefully everyone knows from AS organic chemistry how to draw the mirrored version of this. So you've got your X, Y, and Z axis. You've got a bidentate ligand connected together over here. There's a bidentate ligand over here. In the other side, in the mirrored version, it's exactly the opposite side, just the mirrored. When you mirror it, it's things get laterally or horizontally inverted. So this one is over here. The bidentate ligand is over here. So the two molecules are mirrored versions of each other. No matter how you rotate this, it would never look like this. Just like your two hands. Your two hands, they're kind of identical, but no matter how you rotate one of your hand, it will never actually look exactly like your other hand. So your hands are mirror images of each other. They're non-superimposable. No matter what you do, either your fingers are pointing in the wrong direction, or your palm is facing the wrong direction, or your thumbs are pointing in the wrong direction. The two hands, they just don't look always the same. The same happens with octahedral complexes, but for that, the first version is you need three bidentate ligands to be attached, and there's a mirrored version of that will also have three bidentate ligands attached, but it would be a completely mirrored version, and the two molecules are going to be two complexes, are considered to be two different isomers. They would not be exactly the same. The orientation would always be different. And then there's this version where you can have two bidentate ligands, and on two sides you can have a monodentate ligand. They gave us a different example. I think this one is this part is correct. It's CH2. I mean, the one that they were talking about was, yes, it was NH2, CH2, CH2, NH2 with two water molecules. So instead we have two Cl ligands, so it doesn't make a difference, but the idea is clear. So two bidentate ligands and they're two Cls next to each other, two Cls next to each other. So no matter how you rotate this thing, it would never actually look exactly like this. So the two things are optical isomers of each other. So the two versions that you have to remember. That's the first one. 3 bidentate ligands, or you can have 2 bidentate ligands with 2 monodentate ligands. If you have exactly the same arrangement, they would form non-superimposable mirror images. Is this clear?
Yes, sir.
Okay, so just a quick recap. You've got cisplatin and transplatin square planar. Cls pointing in the same direction, Cls pointing in opposite direction. In octahedral complexes, you can have cis and trans. NH3 is pointing in the same direction, NH3 is pointing in opposite direction. You can also have that if you have 3 ligands of one type. 3 ligands all 90 degrees to each other, or you can have 2 ligands which are 90 degrees to each other and 2 of them 180 degrees apart. So there would be 2 different arrangements of those 3 NH3s. And then you can have cis and trans in bidentate ligands as well. The water molecules could be together, the water molecules could be opposite to each other. And then you had these optical isomers, okay? So that's kind of about it. The very last thing is okay, you've got to I mean that's kind of simple as well. It's define the stability constant, K stability of a complex. Now that's an equilibrium constant, and to perform calculus, describe, explain ligand exchanges. So what this basically means is that whenever you have ligand exchange reactions, all of them are equilibrium reactions. When we studied ligand exchange before, we studied ligand exchange in detail somewhere over here, I think. So we discussed a lot of ligand exchange reactions. Now, most of these ligand exchange reactions are actually reversible reactions. And when they're reversible reactions, any equilibrium reaction or reversible reaction will have an equilibrium constant, and that equilibrium constant is called K stability. So it's just going to take 5 to 10 minutes. So we'll probably do that in the next class, and then we'll do some past papers related to that. Otherwise, it's complete. I mean, K stability is simply that whenever you have a ligand exchange reaction, you got an equilibrium constant, product concentration divided by the reactant concentration. So all these ligand exchange reactions, they're all reversible reactions, and they're all going to have some equilibrium constant, which is known as the stability constant. So we're going to talk about that in the next class. Okay? Does anyone have any questions? Is this clear?
Clear.
Let's continue in the next class. Okay, then take care.
Allah Hafiz.
Allah Hafiz.